This is the applications of Simple Harmonic Motion tutorial. Simple harmonic motion is a term used to describe many different phenomena in our physical world. It's used with all the different types of electromagnetic radiation like light, microwaves, and gamma rays, as well as things like sound waves and the ocean waves. Now before we jump directly into the formula for simple harmonic motion, I want to give you a little bit more information about it. Objects that are exhibiting simple harmonic motion are vibrating, and they're vibrating such that the acceleration of the object is directly proportional to the negative of its distance from the rest position. So what we have here is not necessarily the formula for simple harmonic motion, it's a formula describing the vibration of simple harmonic motion. So the acceleration, that A value, at which that object is vibrating is directly equal to the negative distance that it's vibrating from its rest position, which is that value of x, times the k value, and the k value is a constant that's unique for each individual object exhibiting simple harmonic motion. So let me give you an example of an object that typically exhibits simple harmonic motion. Let's take a look at a spring with a weight attached to the bottom of it. Now imagine that we didn't have a weight attached to the bottom of that spring. It would be scrunched back up to the top. So let's say it would scrunch itself back up to right about here at this level. And we can say that that's about 0.5 meters. Now normally the spring with a weight attached to it would hang right about here at 1.5 meters. However, if you were to apply a force and stretch that spring downward and then let it go, what you'd see is that your spring would bounce up and down, back and forth. Now the distance that you pull it down, or that it comes down with the weight, is down to 2.5 meters, so it goes down 1 meter. And the distance it goes back up to its final position here at the top is 0.5, so again it goes in this direction 1 meter. Now you know that in the real world, eventually this spring is going to come back to rest here at its rest position of 1.5 meters. However, when dealing with simple harmonic motion, the reason we call it simple is because we pretend that this would go on forever, bouncing just like it does, down here to 2.5 meters, then back up to 0.5, and so on and so forth, and it would never stop. So we're assuming that there's no friction present here to keep that spring from stopping in its movement. What we see in real life is what's called damped harmonic motion. And damped harmonic motion means that the harmonic motion has been damped or reduced by some sort of factor. Usually that's friction. But for the case of simple harmonic motion, again remember that it's going to go up and down forever, bouncing in here, and no energy is going to be lost to friction. Now let me show you the interesting way in which this applies to trigonometric functions. To do that, I'm going to go ahead and bring in our unit circle. So here's our standard unit circle. If you go up to the top from our center, which is at 0, 0, you arrive at 0, 1. You've gone 1 unit straight up. And if you go down from the center to the bottom of the unit circle, you get down to 0, -1. So if I were to drop in a little x and y unit axes here, I could show you how this pertains to our trigonometric functions that we've been dealing with. Let me go ahead and bring in the wave that's created by the vibration of this spring and weight attached. So here's something interesting that's created. If you were to imagine that our rest position here at 1.5 meters, if you were to just give it an arbitrary value of 0 units. Now imagine that when the spring is traveling upwards after its downward movement, you're actually going to be traveling along the wave here. And then as the spring comes back down with that weight attached, you travel back down this wave here, back to the rest position, which in this case is 0. Now let's say you continue traveling back down now. You're going to continue traveling back down that wave. And for the purpose of our example, you're going down 1 unit from our 1.5 meter rest position, so you're going to go down -1 to arrive down here at the bottom. And when you max out down there, you're going to be pulled back up by the spring, and you're going to go back up on our function here to your rest position. You're going to continue past it, and you're going to keep bouncing up and down past our rest position, and then back up again past the rest position. You're going to peak out, you're going to come back down to the rest position and keep going, and you're going to go like that forever. And you're going to create this perfect little wave here. So now I think it would be a good time to bring in the formula for simple harmonic motion. So here we have the formula for simple harmonic motion. Simple harmonic motion is x, the distance of the object from its rest position, is equal to a, its acceleration, times cosine of omega t, or x is equal to a times sine of omega t. And the frequency of an object exhibiting simple harmonic motion is equal to omega divided by 2 pi, where omega must be greater than 0. So your first two questions may be, what is omega and what is t there? Well, omega is your angular speed, and t is your time for this equation. So we also have the equation theta is equal to omega times time. And the theta we're referring to is the theta here, the angle that you're making on our unit circle. So you want to keep our theta value in radians. And you can think of this formula, theta is equal to wt, sort of like this formula. Distance is equal to rate times time, because omega is our angular velocity. It's the velocity that we're traveling about this pattern. Now normally this pattern is our circle. In the case of simple harmonic motion, a pattern is a vibration, so in this case, it's going to be an up-down motion. So theta, the distance there, is equal to our rate, so our angular velocity, times our time. Now if you wanted to calculate exactly where you were on the unit circle as you were going around for this simple harmonic motion, you could go ahead and take a times cosine of omega t, or a times cosine theta, to solve for your x-coordinate, and you could use a times the sine of omega t, or a times the sine of theta, for your y-coordinate, because as we know, omega t is theta. Now some people use d for distance when they're talking about simple harmonic motion. I choose to use x, and some people still use x. Just don't confuse x with referring to your relative place as you travel about on the unit circle here. Now for the purpose of your problems here in pre-calculus, your a and your omega are going to be constants. Later on when you're doing these problems in physics, that's most likely going to change. Now with all of these problems in pre-calculus or physics, you're always going to find that your period for simple harmonic motion is going to be equal to 2 pi divided by omega. And the amplitude, so that amplitude for which you go up and down here, for which your motion is constrained, is always going to be the absolute value of your a value. Now there's a lot of information present here. What I want to do is switch us over to taking a look at a practice problem, and you may want to rewind a couple times to see how all this information is connected. So let's go ahead and take a look at one now. I'd like you to write an equation that models the displacement of the weight after time t in the following scenario. Tony adds a weight that pulls a spring down 8 centimeters from its rest position and then releases it. The time for each oscillation of the spring is 2 seconds. Assume that there is no friction present. Now we're told that there's no friction present because that's the only way we can use simple harmonic motion. If friction were present, then we'd be dealing with damped harmonic motion. In these problems, because it's a physics problem and it's also pre-calculus, you always want to draw a figure to go along with the word problem. So I'm going to draw one in now. So you'll notice that I've drawn our spring in here, and then our weight that's attached to it. Now, if you drew that weight down, so if you pulled it down, you could pull it down 8 centimeters like Tony does in this problem. When you release it, it's going to go back up 8 centimeters in the positive direction, and our rest position here is right here at 0 centimeters. So let's begin by writing down what we know. We know that they want us to write an equation that models the displacement of the weight after time, and the displacement being the distance that it's moved. So we're going to take our formula x for the distance, and this is the formula for simple harmonic motion that we're using. X is equal to a times the cosine of omega t. Well, I chose to use cosine because when Tony pulls the weight down to -8 centimeters and then releases, we start our time then. So our time at 0 seconds, the amplitude here, our a value, is going to be -8 centimeters because Tony's holding it down here with his hand at -8 before he lets it go and before we start recording the time. Now the fact that that a is a negative number is going to make this problem a lot easier to just use cosine. Now if you recall our period formula, so we'll just say p, our period, is equal to 2 pi divided by omega, we can use that to calculate our omega. We know that our period for each oscillation, the time it takes to complete it, so to go up then back down, is 2 seconds. So we have 2 seconds is equal to 2 pi divided by omega. So we could multiply by omega on both sides of the equation. On the right hand side they'd cancel, and on the left we'd have 2 times omega is equal to 2 pi. We'd then divide both sides by 2. On the left the 2's would cancel and we would have omega is equal to 2 pi over 2. The 2's would cancel and we'd have just pi. So our omega for this problem is pi. So let's write out our formula now. X is equal to our a value, which is -8, times the cosine of our omega, which is pi, times t. So this equation now is going to model our displacement of our weight here at any time. All you have to do now is use this formula, plug in whatever your time has to be, your seconds, so you could take any time you wanted, and that would give you your x, your displacement. It would tell you exactly where that weight is position-wise. So if you got a positive answer between 0 and 8 for your displacement, you would know that your weight is above your rest position. And if your displacement was negative at the time that you put it in, you would know that your weight is below your rest position. Now you may wonder why something like this is important. Well, imagine if we were dealing with tides right now, and when our displacement was above the rest position, our tide was high. And when our displacement was below the rest position, our tide was low. That would change a lot of different things about what you were considering doing based on whether the tide was high or low. The concept of simple harmonic motion has really far-reaching applications, and it's going to take you a little bit of time getting used to the formula and trying it out in different scenarios to really get a good hang on it. Just remember that when you're dealing with these problems, it's always easiest to draw a diagram and then plug in your given information.